We are live now. Let's start. So we will start with third law of thermodynamics. Now, this third law of thermodynamics is very interesting law, as it says some very interesting facts about entropy. Although second law of thermodynamics also states many things about entropy, but third law of thermodynamics, it has some very interesting observations that we will discuss in some detail in this third law of thermodynamics. So the first very important point that needs to be considered. So third law of thermodynamics talks about temperature that is 0 and not 0 degrees Celsius but 0 Kelvin. So minus 127 like 273 degrees Celsius. So 0 Kelvin. So third law of thermodynamics says that at temperature 0 Kelvin, all energy of thermal motion will be quenched or has been quenched. What it means, we will look at it. And in a perfect crystal, all the atoms or ions are in a regular uniform array. And if we talk about a perfect crystal, and in a perfect crystal, crystal geometry, all the atoms or ions are in a regular uniform array. So let us understand what exactly it means. We know that when the temperature is increased, the internal energy of the system will increase, and because of which the thermal motion, that is the kinetic energy in the particles, it will increase, and the particles will start moving randomly because they will be having energy. And when I will be decreasing the temperature, so the particles, they will start losing their kinetic energy. The thermal motion, it will start decreasing. So the particles, they will start coming closer and closer. And at T is equal to 0 Kelvin, all the thermal motion will be vanished. The particles will not be having any kinetic energy. All their kinetic energy will be given off. And hence, they will be in a state of a like very stable, high stability they will achieve, wherein there will be no randomness, that the particle will not at all be moving. There will be no thermal motion in the particle at T is equal to 0 Kelvin. And if I have a crystalline solid, I know that the property of crystalline solid is that all the atoms or ions, they follow a particular geometry. So at T is equal to 0 Kelvin, the geometry will be perfectly uniform. And it proves that the particles at T is equal to 0, they lose their entropy. No randomness will be there. So this is one very interesting observation we have about T is equal to 0 Kelvin. So in short, what I can say that at T is equal to 0, two main observations what I can see is localization of matter. Since the particle have lost all the thermal motion, the particles will localize. They will come close together. Localization of matter. So this is one property I will see. Localization of matter. Now, second very interesting property I will see is that absence of thermal motion. At T is equal to 0 Kelvin, there will be localization of matter and there will be absence of thermal motion. There will be absence of thermal motion. And both of them will lead to like zero entropy. So at T is equal to 0 Kelvin, we will have zero entropy. So at zero entropy, there will be no thermal motion and the localization of matter will take place. So third law of thermodynamics talks about the state of zero entropy. Now we have one more very interesting thing to discuss. That is the statistical definition of entropy. Like one formula we will discuss. Entropy we have discussed that until now we have discussed the formula for change in entropy. So delta S is equal to delta Q by capital T, the temperature. But now we will be looking at a formula just for entropy. So this is the statistical definition of entropy. And this statistical definition of entropy, it says that entropy S is equal to K log W. Now here, K is the Boltzmann constant is the Boltzmann constant. Capital W, it is the number of microstates. Now, what it means, we will understand. What is the meaning of microstates? We will understand. Capital W is the, it is not the work done. But here in the statistical definition, capital W is the number of microstates. And here the microstates, what it means? It means total number of ways a molecular state can be distributed over the energy states for a specific value of total energy. So the idea is that the particles, they can exhibit in different energy levels. So the in a system, if we have particles, that particles can be different energy levels. So if we have a fixed total energy, so in order to make that fixed total energy, they can exhibit different combinations of individual energy levels, and those different combinations are different microstates. Like if the fixed energy is 10 joule for a system, now that 10 joule can be achieved by different individual energy levels by combining different energy. So those combinations, that snapshot of that, which is giving me 10 joules, every snapshot giving me 10 joule, that is the microstate. So microstate, we got some idea about that. And hence we are talking about statistical definition. In statistics, what we do, all the, like we perform an experiment, and we don't perform an experiment one time, but we perform experiment thousands of times. And whatever results we will get, we will do a statistical approximation of that. Like we will take the mean, average, and statistically we make a conclusion, because we live in an uncertain world. Every time if we perform the same experiment, things will be different. We never know what hidden factor is influencing that reaction, or influencing that process, or influencing that system. So that is why in science, whenever we perform experiments, we perform it many number of times, so that all the hidden parameters also, we take it into consideration in our results. So this is the statistical, and hence statistics is very important in artificial intelligence. Also statistics is very important in machine learning, in data science, and also in scientific studies, like in physics. Everywhere statistics plays a very important role. Now let us just look at one visualization, a very basic one, just for understanding purpose. Like we will have two snapshots, one at 0 Kelvin and one at higher temperature. The idea is very simple, that at 0 Kelvin, system will be perfectly uniform. Everything will be uniform. Just a moment. Everything is, but at higher temperature, there will be disturbance in this uniformity. And that is what is zero, that third law of thermodynamics says. And whenever there is a disturbance in the uniformity, there is an entropy. Whenever there is completely uniformity is there, we say that no entropy, like entropy is zero. But at higher temperature, what will happen? This uniformity will disturb. And it will disturb in such a way that everything will become random. Particles will occupy random positions. Why? Because they will get thermal energy. Because of the thermal energy, they will start moving. Thermal motion will come into picture. And this uniformity will disturb. So this is 0 Kelvin. This is temperature greater than 0 Kelvin. S is equal to 0. S greater. Now, very interesting observation. At T is equal to 0, W is equal to 1. This is very interesting. Number of microstate will be 1. At T is equal to 0, only one possible orientation is possible. That is this. And what will be S? S will be K log 1, that is 0. Because log 1 is 0. Now we will write the statement for third law. Like final. One line statement. The entropy of all perfect crystalline subject substances is 0 at T is equal to 0 Kelvin. So this is the third law of thermodynamics.
Yes, sir.
Now let us do one thing. Now